We have a metallic sphere. Its radius is say 0.08 meters. Its mass is 10 kgs and it's heated to 227 degrees Celsius. This sphere is kept inside a box. This box is at a temperature of 27 degrees. You are given emissivity of this sphere is 1. The sigma is given to be 5.67 into 10 to the power minus 8 watts per meter square Kelvin to the power 4, and the specific heat of this sphere is say 378 joules per kg degrees Celsius. We are supposed to find the maximum rate of temperature drop. This is our question. Let us visualize what is happening. We have this box and its walls are say at temperature 27 degrees Celsius, which is equivalent to 300 Kelvin. This sphere is inside this box. This is heated up to 227 degrees Celsius, which is equivalent to 500 Kelvin. And you are supposed to find out the maximum rate of temperature drop. What we discussed some time back, we found that mc minus mc dt by dt was equal to sigma a epsilon t to the power 4 minus T infinity to the power 4. In this case, T infinity is nothing but the temperature of the box, which is 300 kelvins. The temperature of the sphere is 500 kelvins. Note that this is a variable temperature, but if you look at the expression, the maximum temperature drop is given by minus dt by dt. So minus dt by dt will be maximum if this T is 500. So the maximum temperature drop occurs when the sphere is at its maximum temperature. This epsilon is given to be 1. Area of surface is nothing but 4 pi r square. So it will be 4 pi into 0.08 square. Sigma is given. Mass of the sphere is 10 kgs. And the specific heat is 378 joule per kg per degree Celsius. So we have our equation. What we really need to find out is minus dt by dt. This, if you solve, will give you minus dt by dt to be equal to 0.066 per degree Celsius per second. I would like to point out a few things in this problem. We wrote this expression for Newton's law of cooling. From there, we found out what the constant was, and we had initially separated this in terms of binomial expansion and simplified it. Note that this equation is valid whatsoever, and it does not depend on what is inside this bracket. In Newton's law of cooling, we had a specific condition that the temperature difference between the body and surrounding should be negligible. But in this case, that is not happening. 500 and 300 are pretty large amounts, and the difference between them, 200 Kelvin, is pretty comparable to 500 and 300. So this temperature difference is not small. However, this equation is nothing but the energy balance equation. This is the heat lost by the sphere, and that lost heat is radiated out by that sphere. So the lost heat is radiated out. So what we are having is, there is this body, there is a lot of heat and that is a lot of energy in this body. This heat needs to be liberated out. So that liberated out heat is basically the conversion of this stored heat in form of energy, and this energy is thus ejected out in form of radiation. So this is the energy balance equation. The energy balance equation does not depend on any condition. Energy balance equation is basically an absolute equation. It does not depend on the parameters affecting it. However, if we had variable quantities here, say this part was variable, we were supposed to find out different temperatures, and let's say a temperature is a function of time and etc. We would need to integrate this equation over our required limits, and thus we would get our required answers. Note that this integration is going to be a complex integration. If we split up a to the power 4 minus b to the power 4 kind of a thing, we will be having a complex integration, and the function of temperature as a function of time, or the time as a function of temperature, will be a complicated expression.